All right. Good morning, everyone. We're Team 1. Our project is the Internet on Demand for rural schools in Tanzania. Here's a picture of.
Oh, I'm sorry. One thing. Can you say your names first?
Right. I'm Andrew.
Nick, Steve,
Matt,
Jake.
Okay, and when you start to talk, remind me your names because I want to write down some individual comments.
All right. So I'm Andrew, and like I said, we're Team 1, and this is our project. And here's this is a little picture of some people from where we're going to be going in May. So, next slide. All right, just as an outline of what we're going to talk about today, just a background about the area in Africa, the goals, we're going to outline the goals of our project, an overview of the design we came up with, talk about how and why it's important, and also the risks involved and the costs as well. So, all right, here's a little background about Tanzania. There's some pictures of where it is, and then a little more detailed picture at the bottom. About 40 million people, population. Main languages are Kiswahili and English, and they make most of their money from coffee, tea, and diamonds. And about 68% can read or write, and 96% of the children are enrolled in a school right now. So, all right, a little background about our project. We're going to Mtawambu, which is river of mosquitoes. So we're going to have to wear our mosquito masks all the time over there. There's 4 main schools where we're going. Baraka and Mtawambu are the primary schools, and Manyara and Rift Valley are the secondary schools. Right now, there's internet connectivity at Baraka, Manyara, and Rift Valley. Mtawambu is a primary school that's still being built. Part of our project, I think, may involve us installing the solar panels for power at that school. So each school has 1 computer and 6 monitors. So there's a program on the computer that can split up. So there can be 6 different users on 1 computer. And last year, the team was assigned a similar project, but it didn't work while they went there. So this year we're taking a more simpler and practical approach, and also coming with more than 1 design option. So if one fails, we have more options to take after that. I'll turn over to Matt to talk about some of our goals.
Okay, so our goal is to save power. That's our goal. Because at Baraka Primary School, everything's powered off battery, and the battery is charged by solar panels, so power is a limited resource. What takes the most power is the internet equipment. So as we add more and more schools onto this network, then they're going to want to use the internet. At the same time, we can't have the internet on all the time because it's going to run down the batteries. So we need to save power. These batteries, if they get too low, then it will severely lessen, their lifespan will be shortened a lot. So we can't have the batteries running below a certain level. So we need to monitor the batteries. So all part of this goal of saving power. So now we're going to give a quick run through of the overall design, and then afterwards we go through individual parts of the design. The schools are connected on a network through WiMAX and Wi-Fi antennas. That's the data link. So what the internet's coming in. You see the internet comes in on a satellite receiver, modems and routers. And this side's Baraka, the primary and the first school that's on the solar panels. These would be the secondary schools that are connecting the block. Now originally we're thinking that maybe we could just have, this satellite receiver consumes a lot of power. So maybe we could just have these WiMAX antennas have the network always running, but just not the internet equipment, send a signal through the WiMAX antenna, turn on this part right here. But we found that the WiMAX antennas take a lot of power too, so we wanted to turn those off also when we're not using them. So we went for this FM antenna solution. Have separate antennas, FM antennas, to send the turn-on signal from the remote schools. So it starts in the computer over here, goes to a microcontroller. We're using Arduino to send it to an encoder, encode a signal, transmit it through the FM antennas, receive it on the other side, and then have it decoded and have a microcontroller process it. A microcontroller on the receiving side of Baraka where the solar panels are will control a relay that can determines whether this equipment has power, that turns it on and off. If the battery gets too low, which is powered by the solar panel, then we want to turn everything off too. We don't want to damage the battery. So now Nick will talk about the first step of this.
Okay, so since our whole goal is on-demand internet connectivity for the schools, we have to know when they demand internet, essentially. So, and that's measured by when they're making internet requests from the browser. So you type in google.com, you're making internet requests out into the world, and it comes back to you. Now we have to intercept that request somewhere along the line in order to trigger this whole scheme, so we can actually get everything connected. So the first step of that is installing a software program called Timing Proxy, which is a proxy server that runs on the computer, and it will intercept each and every packet that goes, out from the browser. Browser's configured to use that, and we've modified the source code so that it runs a script which will communicate with an external device outside the computer. Right now, the external device is an Arduino because they're flexible with prototyping. If we need to, we're going to simplify into a more low power, more durable circuit later. And it's also, Arduino is very flexible for this because we have an Ethernet attachment for it. So if we add multiple computers, we can modify it so it can run over the network instead of connected directly to the computer over serial. But right now, it's connected just via USB to the computer, and from the Arduino goes to the rest of the circuit. So when typing, whatever internet address, it triggers the Arduino, which sends a quick pulse. Hey, I'm here. Let's turn this whole thing on. Very simple. I'm Nick Parker.
I'm Jake. As Nick said, we're using the Arduino to power on the encoding chips. One of the reasons we don't leave the chips on all the time is they don't use too much power, but the schools that they're at, they are on the power grid, but power is pretty expensive for them, so we try and minimize that as much as possible. One of the goals we haven't mentioned yet for the design was to create a system that we can implement in other schools, not just the ones that we're installing this summer. And with the encoding chips on the right over there, we're able to create 256 unique signals that can be decoded by the decoder at the main school, which allows us to turn either the Wi-Fi or the WiMAX and not both the systems, so we can save more power. Next slide. And to send and receive the internet request signal, we're using Yagi array antennas at both the school, or all three of the schools rather. There's a large gain associated with them. There's a small length. We looked at using different frequencies that have a larger wavelength, so a larger antenna, but they were, I think, about 30 feet long, so bringing them over to Africa on an airplane and also installing them with our limited space would have been an issue. We went with a 433 megahertz band. It's low loss. We're sending around a 5-volt signal through the air, so there won't be too much dispersion of that signal, so we can successfully decode that. And line of sight, there's obviously a lot of trees in Africa, especially between the schools. But the waves are able to propagate through those trees pretty well with this frequency. And it's also an unlicensed band in Africa, so we won't have any issues with their communications systems. And Steve's going to take over the rest.
So why are we going to use ECE? Personally, I wouldn't want to use them, but they're extremely low power, and they're designed specifically for solar power applications. And what's going to happen is a user at a remote school is going to make an internet request, and the TCP packet's going to come over to our side Baraka, and the PSOC is going to have to wake up from sleep, process it, turn on the satellite and so forth, and then go back to sleep. And PSOC will be running maybe 5 minutes a day, if even that. And the advantage to this is that it can still be on and monitor the battery levels and the TCP request. And it has a real-time clock, so we can time out if the user doesn't do any activity for 15 minutes. As we said earlier, the biggest thing we have to worry about is very low power. And like last year, they had a design, it worked, it was good, and they went over there and put it in, and it did not work. And we're trying to over-engineer something this year. And it might not be the prettiest solution, but it has to work. And it has to do the job well. And because we're in the States and it's a different continent, we need to make sure that you can keep it up and maintain it, because they're not really engineers over there. And I'll talk about the cost in the next slide. Maybe not. All right, so we can design this, test it in lab, go outside, and it can work. But then when we go to Africa, we can't take into consideration or even think about stuff like rats. And we can set up the equipment, but we're gonna have to run cables, maybe through the attic or on top of the roof of a one-story building. And we were told that last year, the internet didn't work, and they didn't know why. They went over there, and the equipment was all fine, and then they found out that rats had eaten the cables. And this year, we're gonna have to cover that up and hide it and make it a little more hidden. And another thing we have to account for is children. It's for a school. We can't have open electronics. We have to make them contained. We can't have wires going everywhere. And the terrain's also another big thing. There's sand, there's dirt. I have no idea what else, but it can get in the equipment and damage it. And when we were looking at the equipment that they brought up back from last year, it was extremely dirty, and it's something we never would have considered. Okay, so as you can see, the cost is really relatively cheap, and that's because we are reusing components from last year. And we are going to buy a second antenna, even though there are antennas already there, and that's only because we want to make sure our design works. And we're going to bring that over just as a safeguard if something over there is not working. But the Linux is a free operating system. The Arduino is really cheap, and the PSOCs were donated. And I guess that's all. Any questions?
Any questions from the class? Try to think of a question to ask each team. So since nobody did it, I'll ask a question. What about bandwidth considerations? Are there bandwidth requirements that you have to meet? And at that 433 megahertz frequency, are you going to be able to meet those bandwidth requirements?
As far as we know, there's not really a lot of communication in Africa with that band. It's an unlicensed band over there. Cell phones operate on different frequencies. So last year's team, we know that they didn't have any issues with any interference between other signals. So we're hoping that's still the case.
Okay. Any other questions? Okay, these guys went first, so we have to give them credit for it.